Hello, welcome to example 2 and 3-3 solving systems of linear inequalities. We are getting closer to the main idea of this chapter 3 section. And for this, let me switch my light a little bit, make it a little brighter. For this one, I do not want you to be intimidated by the application problem. All right, this is what we're leading you up to, making sure that you understand how to do this stuff, okay? When we say, when are we ever going to use this? I know. It's in real life applications that involve science, technology, engineering, in this case navigation, where we're going to be using the math that we have. Okay, you don't use all math in every place, okay? But you do use some math in every place. So I will talk you through this first one. Watch it a couple times if you need help and ask questions in the discussion. All right, so here's the situation. We have a polar expedition. It's dangerous, okay? It doesn't really say whether it's North Pole or South Pole, right? Doesn't matter. We have a polar expedition, and it's 240 miles away at that moment from the base camp. And a snowstorm is predicted to reach the area in 48 hours. That means by 48 hours, the storm will be there. Maybe sooner, but not after. Maybe sooner, okay? So by 48 hours, you'll be in the storm, and that storm may have already occurred. So the storm might actually show up in 3 hours. Keep that in mind. That's going to be important. The expedition is going to travel as far as possible by boat, because so I guess we can assume we're in the North Pole, but yeah, you can travel by boat on the edges of the South Pole continent. Doesn't matter. And when the boat gets stuck, probably in ice, they're going to walk the remaining distance to camp before the storm hits. So not only do you get some math problems in here, you got like a real exciting story. I love it. Now, these explorers can navigate the boat through the ice at a rate of 12 miles per hour. That's information we're going to come back to. Or they can walk with the equipment at 3 miles per hour, which I think is actually pretty fast to walk in snow carrying equipment. I think 3 miles per hour is about what I do when I walk my golden retriever. But these guys are superstars. Write and graph a system of inequalities that can be used to determine how long they were going to travel by foot or boat to reach the base camp. All right, we have two inequalities. It tells you at the end what to look for. It tells you, we have two variables. It tells you what to look for. Write and graph a system of inequalities that can be used to determine how long the explorers may travel by foot. Okay, and when they say how long, they're talking about time. So I'm going to let X represent the number of hours that the explorers are going to walk. And how long is it going to take to go by boat? So I'm going to let Y represent the number of hours that they're going to travel by boat. And where did I get that from? It's directly from the question. The question is going to tell you what to find. Those are your variables. Now we got to come up with the inequalities. Let's pick the first one. If they're going to walk a little bit, and if they're going to if they're going to boat, the total time is going to be how many hours they walk plus how many hours that they're going to be on the boat. So that's going to be X plus Y. This is going to be the total number of hours that they're going to travel, either by walking or by boating. The storm is going to hit in 48 hours. Now, I mentioned when I read it, I said that doesn't mean exactly 48 hours. It means that it could be less than 48 hours, but not longer than that. All right? Now, a little bit of an aside. I don't think that like meteorologists are that accurate, but we're just going to go with it, okay? So this is going to be less than or equal to 48. That's my first inequality. The total amount of time has to be less than the 48 hours they have until the storm hits. Pause it if you need to, rewind it if you need to. Now let's talk about the distance. The expedition is 240 miles away. Okay, how far are they going to walk in X hours? Well, I said I was going to remember that, okay? They can walk at 3 miles per hour. So after 1 hour, 3 miles, 2 hours, 6 miles, 3 hours, 9 miles. You get it. What am I doing? I'm multiplying by 3. So for the distance, how far are they going to walk? It's going to be 3 multiplied by the number of hours that they walk. How far are they going to boat? The boat goes 12 miles per hour. So that's going to be 12 multiplied by the number of hours. Remember, X and Y represent the time, the number of hours that they walk or boat. I'm going to add these two together because that represents the total distance. But now here's the tricky part. If they go in a straight line, of course, you got the curvature of the Earth, so you can ignore that for a second. But if they go directly in what we in geometry call the Great Circle Arc, but if they go directly, they're going to go 240 miles. They cannot go less than 240 miles. But they could go more than 240 miles. Why? They might get lost. They might have trouble with their navigation, or they might have to go around some sort of natural feature. So instead of going from like a straight line from where they're at to the base camp, they might have to go a little bit further. So this distance could be greater than or equal to 240. So now we're going to graph that, and I need a separate sheet of paper because my graph is kind of big. But first I'm going to write this down. X plus Y is less than or equal to 48, and 3x plus 12y is greater than or equal to 240. I'll move that out of the way. All right, so let's graph that. So both of these are in standard form, so I'm going to use the intercept method, which we also talked about in chapter 2, section 5. All right, if my boundary line is x plus y equals 48, that tells me if I let x equal 0, y equals 48. 48, and I had to make my scale kind of big here. Here's 40, 42, 44, 46, here's 48. And if I let my y equal 0, my x is going to be 48. So my x-intercept, 2, 4, 6, 8, is right here. And I usually try to draw these freehand, but I think I'm going to need a ruler for this. Alrighty? Oh, and since it's or equal to, I'm going to draw a solid line, because it's possible that the storm could show up in exactly 48 hours according to the prediction. So I'll draw this just like that, and there you go, there's my line. And you're probably wondering, but wait, you said always go off from one edge to the other edge. That is absolutely true, but not here. Why? Because what do these represent? My x represents, I should have done this at the beginning, this is the number of hours that the expedition is going to walk, and this is going to be, I'll write it sideways, the number of hours that they are going to be in the boat. And since time is not negative, I have to stop when I get to my zeros. Okay? All right, now for the other one, my boundary line is 3x plus 12y equals 240. So if I let x equals 0, I get 12y equals 240. And I get y equals 20. So y equals 20 is right here. There's something I forgot in the other problem. I'll do it when I get this one done. You probably noticed while I was doing this, okay? If I let y equal 0, I get 3x equals 240, and I get x equals 80. And I didn't make my graph big enough for that, so it'll be okay. We'll figure it out. All right? Just gotta double check. I'm gonna switch over to Desmos on this one, okay? All right, and again, this is going to be a solid line, and my solid line is going to go this direction. So 80 is going to be like over here someplace. So hopefully I had like a better graph, right? But it'll be okay for our purposes. I want to check one point real quick before we do this. I guess I could try something else. I could try x equals 10. And if I try x equals 10, I get 30 plus 12y equals 240. And I'm going to do some math here real quick. So, yeah, I didn't realize that my graph was going to go off. Yeah, it's going to be it. Hang on. 210 divided by 12, about 17.5. So 17.5 would be about, here's 16, about right there. So yeah, I just need another point so I know which direction it's going to go. And that's going to look like this. And of course, somewhere out here it's going to be heading toward 80. Okay. Now this is the thing that I told you that I forgot. I am going to shade below this line. All right. So if I pick some points and I figure out where I'm going to shade, I'm going to be shading like right here, like this. I'm going to start it off like this. And again, I can pick a point on either side, or I can just subtract x from both sides and realize that I've got the less than, so I'm shading below it. For the other one, if I pick points or if I solve for y, I'm going to be shading above it. So this one's going to be like this. And it looks like this area right here is going to be my overlap. Okay, so the last question in this is going to be, does the point 15, it's that evening time when we get phone calls. We're getting lots of vote for me phone calls. So this is going to be 15 hours walked and 25 hours by boat. Is that going to work? So let's find out where 15, 25 is. So here's 10, 12, 14. Here's 15 right here. And 25 is right here. So I'm going to go up right there. This point is 15, 25. So it is in the overlap. So if they need to walk for 15 hours and be on the boat for 25 hours, it's going to meet the requirements, and they're going to get there in the constraints that they have. Okay? See you in the next video.